Okay, hello everybody. This is the A-level cookbook, Recipes to Survive A-levels, and today we're going to be talking about the dreaded topic, electrode potentials. So the topics we'll discuss today are electrochemical cells, how to draw electrochemical cells, half equations and cell diagrams, electrode potentials, standard electrode potentials, electrochemical series, and using cell potentials to predict reaction outcomes, and batteries as well as fuel cells. So it's a quick whistle-stop tour of all the things you need to know. So let's get started with the fundamentals then. So electrochemical cells use redox reactions to generate electricity. As a reminder, reduction is where something gains electrons, oxidation is where something loses electrons. And you can remember this using oil rig, where oxidation is losing OIL and reduction is gaining RIG. We can make electrochemical cells by connecting two different metals dipped in salt ions of their own solutions and connecting them with a wire known as the external circuit. So that's the wire where the electrons flow through and power whatever it is that needs powering. And as a reminder, electrons flow towards the positive electrode and away from the negative electrode. A way of remembering which one is the anode and the cathode is by anode attracting negativity and cathode attracting positive ions. The T in cathode kind of looks like a plus. So let's take an example then of an aluminium and a copper electrochemical cell. You can dip an aluminium electrode in a salt that dissociates into Al3 plus ions and a copper salt that dissociates into Cu2 plus ions. Aluminium oxidizes more easily than copper, so it releases electrons into the external circuit. We will discuss how you're able to tell this later on in the video. The copper ions are reduced using these electrons and forms solid copper, as you can see in the diagram. You can see this here, where the solid aluminium is oxidized and loses electrons to form Al3+. The electrons it loses flows through this external circuit and then goes into this solution here. It combines the copper ions and reduces it to form solid copper. In electrochemical cells, we also use a salt bridge to connect the two. So this is usually filter paper soaked in potassium nitrate. The reason for this is because it allows ions from the salt to move between the half cells, balance out the charges, and complete the circuit without these two reacting with each other. Without a salt bridge, one side would accumulate a negative charge and the other side would accumulate a positive charge and the reaction would just stop. The ions in the salt bridge balance the charges between the two and it allows the reactions to continue and hence the flow of electrons as well. And we can use a voltmeter to record the voltage or potential difference between the two cells. This gives us the cell potential or EMF. And here's an animation showing the movement of electrons and the involvement of the salt bridge as well. So you've got your electrons moving through the circuit, and you've got your salt bridge balancing out the charges. Okay, so when designing electrochemical cells, the electrodes are usually salts that conduct electricity, and they're usually the metal of interest. However, sometimes we're in scenarios where the ions involved can't be a solid. So when we have that scenario, we use platinum instead. And an example of this is when we have half cells that have solutions containing ions of the same element. An example is Fe3 plus and Fe2 plus here. So we're not going from solid Fe to, these ions here. We've actually got Fe3 plus going to Fe2 plus and vice versa. So we can't really use solid Fe as an electrode. So in these scenarios, we use platinum instead. The reason being is because it conducts electricity but is inert, it doesn't really react with anything. And the conversion between the ions happens on the surface of the platinum. So on the surface of the platinum, the Fe3 plus might be reduced into Fe2 plus, or it might be oxidized from Fe2 plus into Fe3 plus, depending on what the other half of the circuit entails. So when it comes to drawing electrochemical cells, we can draw them in the way that those illustrations showed, but we can also use something called the conventional method as well. So this is where the half cells are arranged in a row with the reduced forms of each species on the edges and the oxidized forms in the middle, separated by a vertical line. So I know I've just said a lot of words there, but I'll show you a diagram and it'll make more sense. So when drawing electrochemical cells using the conventional method, we put the more negative electrode potential on the left. So for example, if we have a zinc-copper electrochemical cell, zinc is more negative. Again, we'll talk about that later and how you decide which is which. And this is what it would look like. So you've got the zinc half cell on the left and the copper half cell on the right. This one's more negative, so it's on the left, negative, left. And as well as that, you've got horizontal lines that separate the different ions, and you've also got the two here representing the salt bridge. And as well as that, you've got your reduced forms on the outside. So zinc, when it has those electrons, becomes solid zinc rather than Zn2+. So it's reduced and it's on this side, whereas it's oxidized to form Zn2+, so it goes in the middle. Likewise with copper, solid copper here is on the right, it's on the outermost part, but when it's oxidized to form Cu2+, it goes in the middle. And again, the two lines in the center represent the salt bridge. So another rule with the conventional method is that substances in the same phase are separated by a comma instead. So for example, let's say we have a zinc-iron electrochemical cell. The zinc is more negative, so it goes on the left. As always, you'd write your more negative electrode potential on the left, but since the equation for iron involves Fe2 plus and Fe3 plus, we use a platinum electrode instead. This is just added at the end of the diagram, separated with a vertical line. Again, because we're exchanging between ions of the same element, they can't be solid, so we use a platinum electrode. And because they're in the same phase, we need to separate them with a comma instead. So this is what the cell would look like. You've got your reduced zinc on the outside, it's got the electrons and it's lost them here, the oxidized form in the middle. And then over here, you've got your ions separated by a comma because they're both aqueous, they're both in the same phase. Like every single electrochemical cell in existence being drawn in the conventional manner, we put the reduced form on the outside. So this Fe2 plus has more electrons than the Fe3 plus, it's reduced, so it's on the outer part, whereas the Fe3 plus is in the middle. Because we're dealing with ions of the same element, these can't act as an electrode, so we need to use the platinum one, which is just written here like this with a line separating it. So let's talk about what electrode potentials actually are and their relevance. So oxidation and reduction takes place in each electrode of a cell, and these reactions are actually reversible. So if we take a magnesium copper cell, the following reactions happen. So you've got magnesium ions being reduced into solid magnesium, and you've got copper ions being reduced into solid copper. Now you can see they've given us some voltages here. These are the electrode potentials. Now, which way the reaction goes depends on the electrode potential, and it depends on which two metals you've used. If one of the metals has a more negative electrode potential, that one is oxidized, and the other one must be reduced, because when you have oxidation, there must always be reduction as well. And if you think about it, it does make sense, because when you have oxidation, you're losing electrons. The electrons are being given to the circuit, so it would make sense for the electrode potential to be more negative. And again, this helps us decide which way the reaction is going. So using this example here, the magnesium has a more negative electrode potential, so it's being oxidized. So this equation should actually be written as Mg solid going to Mg2 plus 2E minus. And therefore, this copper has to be reduced so this stays as is. So based on this example, we can deduce the following. We can say that magnesium is being oxidized because it's more negative, and we can deduce that copper is being reduced. Now, we need to decide which is also the anode and cathode. So oxidation happens at the anode, reduction happens at the cathode. A good way of remembering this is an ox, red cat. So anode, oxidation, cathode, reduction. And again, that makes sense because anode is negative and you're getting oxidation, which is releasing electrons into the circuit. So that forms a negative electrode. And they're moving towards the positive electrode, which is the cathode, which is where reduction happens. So let's talk about using electrode potentials and their relevance to electrochemical cells. A good way to do this is to just do a practice question. So let's say we have this example. We have two half equations with these electrode potentials. We've got aluminium and we've got silver. Draw the conventional representation of this cell. So I'll let you guys have a try first, and then I'll show you the solution. Just pause the video and then press play when you're ready. When drawing the conventional representation, the more negative electrode always goes on the left, and we just said that the more negative electrode potential is also being oxidized. So first, decide which equation is being oxidized and which is being reduced. So the aluminium half equation has a more negative value. You can see that's minus 1.7 volts compared to plus 0.78, so that has to be oxidized. So we rewrite the equation to show it being oxidized. So you can see we've got Al3 plus 3E minus. This is reduction because it's gaining electrons. So we need to rewrite this equation to demonstrate oxidation. So that would be aluminium solid goes to Al3 plus 3E minus. It's losing electrons. Because this is being oxidized, the silver has to be reduced. So that equation would just be Ag plus E minus going to Ag solid. So now we've decided which one's more negative and which one's more positive. Remember that the more negative half cell goes on the left and the oxidized parts go in the middle. So you have something like this, where you have the more negative half cell on the left and the more positive one on the right. The reduced forms on the outside. So this has the electrons, and when it's oxidized, it forms Al3 plus. And this has the electrons. When this is oxidized, it forms Ag plus. So the reduced forms are on the outer part. They're all in different phases, so we don't need to use any platinum electrodes. So we don't have ions of the same element either. So let's take another example. A conventional representation of a nickel-copper cell is given below. So here's the representation. Determine the half equations for the reactions happening at the positive and negative electrodes of the cell. So I'll let you guys try this. Just press pause and then press play when you're ready. So as always, try to determine which one's more negative and which one's more positive, because remember, if it's more negative, it's oxidizing, and if it's more positive, it's reducing. So in conventional notation, the left side is more negative and the right side is more positive. The more negative half equation is oxidized, therefore the more positive half equation has to be reduced. So this leaves us with NiS going to Ni2 plus Aq plus 2E minus. It's being oxidized because it's on the left. It's losing electrons. And this has to be reduced. Cu2 plus 2E minus going to copper solid. The cell potential can be measured using a voltmeter, but it can also be calculated using this formula as well, where we have E cell equals E reduced minus E oxidized, which is equal to E right minus left. Sorry, this is a formula you will need to memorize. The conventional representation of the zinc copper electrochemical cell is shown below. The standard electrode potential of the zinc half cell is minus 0.78 volts, and the standard electrode potential of the copper half cell is plus 0.35 volts. Calculate the EMF of the cell. I'll let you guys just give this a shot, and then once you're done, just press play. Let's draw the conventional representation of it. So the zinc is more negative, so it's going to go on the left, and the copper is more positive, so it goes on the right. So it should look something like this. Again, your reduced forms on the outside, and the oxidized forms on the inside. The formula says that it is reduced minus oxidized. So what's being reduced is the copper half cell, which is 0.35, and we're subtracting minus 0.78. Remember that a minus and a minus makes a plus, so you're left with 1.13 volts. Okay, so let's try another example. The conventional representation of the magnesium-copper electrochemical cell is shown. The standard electrode potential of the magnesium half cell is minus 2.40 volts. The cell has an EMF of 2.8 volts. Find the electrode potential of the copper half cell, and here's the conventional representation. I'll let you guys have a go at this, and then just press play when you want to see the answer. It's helpful to start off by writing out the formula for the EMF of the cell, which is reduced minus oxidized, or right minus left. So we want to find out the right side, which is copper, which is being reduced. So we need to rearrange this formula. So E cell plus E oxidized gives us E reduced. And then what you do is you just stick the numbers in. So E cell is EMF 2.8 volts, plus the EMF of the oxidized side, which is minus 2.40 volts. So that's 2.8 plus minus 2.4, and that gives you 0.4 volts. Remember, the signs are very important in this. Let's talk about standard electrode potentials. So I gave you all of these electrode potential numbers, but where did they actually come from? This is where the standard electrode potential comes in, and this involves using a standard hydrogen electrode as a half cell. So since electrode potentials are equilibrium reactions, measuring and comparing different values can be quite tricky because they're affected by temperature, pressure, and concentration. And as well as that, it varies depending on what half cells you have. If you have zinc and copper, that's going to be different to something like aluminium and copper. So to overcome this, we measure the EMF using a voltmeter of what we want to test against a standard hydrogen electrode. So if I want to know what the standard electrode potential of aluminium is, we test it with this standard hydrogen electrode as one of the half cells and the aluminium as the other. So how the hydrogen half cell works, hydrogen gas is bubbled into a solution of H+ ions. And so because we're using H2 and H+, the same element, but we're switching from an element to an ion, we need to use a platinum electrode for the reactions to happen over. Because the electrode potential varies with concentration, temperature, and pressure, if you were a scientist trying to record the electrode potential of aluminium, for example, and you did it in a room that's really, really warm, your number's going to be different to mine. So to overcome this, what we do is we measure these standard electrode potentials under standard conditions. So the temperature must be 298 Kelvin, the pressure must be 100 kilopascals, and any solution that you use must have a 1 mole per decimeter cubed concentration. So let's talk about how you actually would measure a standard electrode potential. So you set up an electrochemical cell using hydrogen and the ion of choice, and then you measure the EMF under standard conditions. So for example, if I have this metal M here, I connect a metal M half cell to a standard hydrogen electrode, and then I measure the voltage between them, provided that the conditions are met. So we've got 100 kilopascals of pressure, we've got 1 mole per decimeter cubed of both solutions, and it's happening at 298 Kelvin. Then and only then can I measure what the standard electrode potential of this would be. And now let's talk about how you actually calculate that. Let me use zinc as an example. So if we have a standard electrode potential with zinc, the conventional form would look like this. So we've got hydrogen on the left, we've got zinc on the right, and because we're using H2 and H+, and the same element, we need to use a platinum electrode. Whenever we're working out a standard electrode potential, we always set the hydrogen electrode potential to be 0. So since E cell equals E reduced minus E oxidized, which is right minus left in this case, E cell equals E right, because the left has become 0. So just as a quick summary, those numbers that I was giving you of this many volts and whatever, it all comes from standard electrode potentials, which is where you get the metal you want to test and put it against a standard hydrogen electrode, make sure the pressure is 100 kilopascals, make sure the temperature is 298 Kelvin, and make sure all solutions are 1 mole per decimeter cubed, and then that's what gives you that number. And we can use those numbers to set up electrochemical series. So an electrochemical series is just a big old list of electrode potentials in ascending order from the negative down to most positive. So here's an example. So you can see the EMF values here from negative to positive, and you've got all of these half equations. The half equations are written as reversible reduction equations. It's just for consistency, because if you had reduction here, oxidation here, it just gets a bit confusing. We can use the half equations in electrochemical series and combine the different half equations to predict how an electrochemical cell will behave. When we do this, we need to decide which one's being oxidized and reduced, and like before, the one that's more negative is oxidized and the one that's more reduced is positive. When combining them, all we do is decide that, balance things out, and rewrite the equations, and we'll do a couple examples. So let's talk about using an electrochemical series. We can use electrochemical series to make electrochemical cells and predict whether the reaction will happen or not. So here's an example of the electrochemical series from before. So whenever we're doing this, first of all, we need to find the actual half equations we want to test. We need to decide which one's being oxidized and which one's being reduced. So again, more negative is oxidized, more positive is reduced. We balance the number of electrons in both equations, and then you combine them and just remove anything that's unreacted or known as spectators. Then you calculate the EMF by doing E cell equals E reduced minus E oxidized, which can be remembered as redox. Redox. And you need to interpret the EMF as well. So if the EMF is positive, the redox reaction is feasible. However, like I said before, these are reversible reactions, so they can be affected by temperature, pressure, and concentration. So the reaction may not be feasible at a certain temperature, for example. So that's something to just keep in mind. So let's try an example. Work out the EMF of a lithium-copper electrochemical cell. And here's the electrochemical series as well. Give this question a try, and then press play when you want to see the solution. So there's lithium in this, so we want to pick out the lithium equation, and there's copper, so we're going to pick out this copper equation. And I've put the electrode potentials next to them as well. We need to now decide which one's oxidized and which one's reduced, and then rewrite them. So the lithium's more negative, so that one's being oxidized, and the copper is more positive, so that's being reduced. We're going to rewrite the lithium equation to show oxidation, which is this, and we're going to rewrite the copper equation to show reduction, which is actually just the same as here. Next, what we need to do is we need to balance the equations. So I'm going to multiply this by 2, so we get 2 electrons here. So you've now got 2 Li goes to 2 Li plus and 2 E minus, and the copper one stays the same. Combining these two gives you 2 Li plus 2 Cu2 plus 2 E minus goes to a 2 Li plus Cu solid and 2 E minus. And then all you do is you just remove the things that are on both sides. So we've got electrons on both sides, so off they go. Now, obviously, the question wants us to work out the EMF of this cell. Oh my god, all we do is we just work out the formula, which is just E cell equals E reduced minus oxidized, which is just slapping the numbers in, and it should give you 3.35 volts. And also, in some questions, you might need to interpret the EMF. The EMF in this case is positive, so this reaction is feasible. So here's another example of a question you might see. Determine whether the following redox reaction is feasible or not. So you've got CuS plus Zn2 plus aqueous going to Cu2 plus aqueous plus Zns. And here's an electrochemical series. I'll let you try this question and then just press play when you want to see the solution. So as always, pick the equations of interest. So we're looking at copper and we're looking at zinc. So we're going to pick those two equations out. We now need to decide which one's being oxidized and which is being reduced. However, in this question, they're telling you what it is. So don't just jump to which one's more negative, which one's more positive. But this time they've given us an equation. So we need to follow what they determine is oxidized and which one's reduced. So we can see here in this full equation that the copper is being oxidized because it's going from solid copper to Cu2 plus, it's losing electrons, and the zinc is being reduced. It's going from Zn2 plus to zinc solid. So we don't look at the whole like, oh yeah, this one's more negative, because in this case, they've given us what the equation is. They're testing this scenario, seeing if it works. So what we do is we work out the EMF using the numbers they've given us in the way they want it. So again, we've determined that the copper is being oxidized and the zinc is being reduced. So the EMF formula is reduced minus oxidized, which would be minus 0.75. The zinc is being reduced minus the oxidized copper, which is plus 0.35. And that gives us a value of minus 1.10 volts. So we need to interpret this. The EMF is negative, therefore this reaction is not feasible. So sometimes they might give you questions where they've given you an equation and they want you to test whether it works. In these scenarios, you don't need to do the whole like one's more negative, therefore that one's being oxidized sort of thing. You work on what they've given you. Let's try an example. Some electrode standard potentials are shown below. I'm not even going to read all of these out. Here you go, enjoy. All right, so we've got 4 of them. An electrochemical cell is constructed using reactions 1 to 4. Draw this electrochemical cell in its conventional form and calculate its EMF. So I'll just let you have a go. Press play when you want to see the solution. Okay, so as always, determine which one's being oxidized and which one's being reduced. So in this case, we're looking at reactions 1 and 4. And between 1 and 4, the reaction involving aluminium is more negative. so that one's being oxidized. So I'm going to rewrite that equation to show oxidation. So we're going from solid aluminium to Al3+, losing electrons. And the copper is being reduced, so I'm going to rewrite that in the form of it being reduced. Next, we draw the conventional cell. Remember that the negative goes on the left, so this is what it should look like. And remember, your reduced forms go on the outsides, and the oxidized forms go on the insides. And then you just calculate the EMF using the formula, E cell equals E reduced minus E oxidized, which should give you 2.01 volts. Okay, so here's another example for you to try. We've got a bunch of electrode potentials here in an electrochemical series, and an electrochemical cell is constructed using reactions 3 and 4. Write the overall equation for this electrochemical cell and calculate its EMF. So give it a shot and then just press play when you want to see the solution. Okay, so this one's a relatively spicy question, but if you just follow the basics, it's fine. So determine which equation's being oxidized and which one's being reduced. So we're looking at equations 3 and 4. If you look at equation 3, that one's more negative compared to this. Obviously, this is more positive, it's higher, and this one's smaller, so that has to be more negative compared to each other. So that means we're going to rewrite equation 3 in the form of it being oxidized. So we're going from 2Cr3 plus with 7H2O to this. Equation 4 is obviously being reduced, so we write it in the form of it being reduced. And again, since electrochemical series usually write reactions in the form of reduction, oxidation is just the opposite. So next what we want to do is we want to balance the electrons in both equations. So we've got 6 electrons here and 3 here, so it would make sense to times this whole thing by 2. So we get 2 times that whole equation, and then all you do is you just combine both equations, which gives you this very, very lovely long line. And then what we do is we remove all the unreacted stuff. So here's our lovely, lovely long equation, and I've highlighted everything in red that needs sort of adjusting. And then we're left with this. So you can see that the 16H plus is on this side and 14 here, so we can take all 14 away here, and that leaves 2 on this side. There's 6 electrons on both sides, so those can all disappear. And we're left with 8H2O and 7 here. All 7 of these disappear, and 1's left here. And then next what we do is we calculate the EMF using the values of that electrochemical series table, and that gives us a sweet value of 0.87 volts. So here's another example. We've got some more electrode potentials here for you to use, and it says determine whether the following reaction takes place or not. Have a go, and then press play when you want to see the solutions. So again, in this case, they've told us what's being oxidized and what's being reduced. We're not looking at what's more negative here, we're using what they tell us. So in this scenario, Al3 plus is being reduced and the V2 plus is oxidized, because if you see, the Al3 plus has become Al solid. It's gained 3 electrons. And this is being oxidized as well, because it's gone from V2 plus to V3 plus. Therefore, E cell equals E reduced minus oxidized, so we stick the numbers in using the table, and it gives us minus 1.92 volts. Since the EMF is negative, this reaction does not take place. Let's talk about the uses of electrode potentials on electrochemical cells, and this is batteries. So commercial cells can come in 2 different types. You can have non-rechargeable cells, and these use non-reversible reactions. And an example is the dry cell alkaline battery. Rechargeable cells use reversible reactions, and an example of this is the lithium cell. So let's discuss more things about non-rechargeable cells. So they use irreversible reactions, and an example of this is the zinc-carbon dry cell. You've got your 2 equations here, and based on the whole sort of, deciding which one's more negative, which one's being oxidized, blah, 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 you get this as your whole equation. And if we use the formula to work out the EMF, you get E cell equals E reduced minus oxidized, which is 0.76 minus 0.8, which gives you 1.56 volts. The reason that non-rechargeable batteries are so is because trying to reverse the reaction isn't really practical. Trying this might cause the cell to leak or explode. Now, sometimes what they do is they actually make the casing out of one of the metals used. So if they become ions through oxidation, that can actually wear down the casing and make it leak. Let's talk about rechargeable cells. So these use reversible reactions, and an example is the lithium cobalt oxide cell. So here's our 2 equations here using reversible reactions. If you do the whole negative this, that, blah, 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 and combine them, this is what you get. And if we work out the EMF, it gives us a nice hefty EMF of 3.50 volts. So we can recharge rechargeable cells by applying a current to force electrons in the opposite direction. This doesn't really cause much of a problem because in a rechargeable battery, they don't actually form part of the casing, the stuff that's used, and also nothing escapes or is used up. And last but not least, let's talk about the dreaded fuel cell. So this differs from electrochemical cells because in electrochemical cells, the chemicals that are needed are always in the electrolytes and in the solution. Fuel cells generate electricity when the fuel is stored outside of the cell and is fed in when it's needed. So a key example is the alkaline hydrogen fuel cell, which I've tried to simplify using this animation on the right. So how this works is that hydrogen and oxygen is fed into 2 platinum-coated electrodes. The electrodes are separated by a membrane that only allows OH- and H2O through, but not H2 and O2. It also contains an aqueous KOH solution as well as the electrolyte. So how it works is hydrogen is fed to the anode, which is on the left, and then the following reaction takes place. And as you can see, this generates electrons here. The electrons flow from the anode through an external circuit to the cathode. And you can see that here because you've got your hydrogen coming in here. It reacts with the OH minus and it generates electrons, which flows through into the cathode. OH minus passes through towards the anode. On the other side, on the cathode, oxygen is fed and this reaction takes place. Combining both of these gives us an overall reaction of 2H2 plus O2 gives you 2H2O. So you can see hydrogen's fed here, it does this reaction and it forms electrons. The electrons move around here to the cathode, and on the other side, the oxygen reacts with water and these electrons to generate OH minus, and that OH minus moves across, and that OH minus comes over here and reacts and generates water. Again, this is just an overly simplified diagram, and it's not perfectly balanced, but it kind of gets it across. So I know that's been a very fast tutorial. If you guys notice any sort of mistakes or errors, let me know, and if you have any other questions or concerns, feel free to drop me a comment or an email. And if you found this video helpful, feel free to share it because that goes a long way, and thank you very much.